Good day, Dr. Nordin and everyone. So this is the assignment one, individual assignment of fluid mechanics, and my name is Siow Yu Ki, matrix number 225639. So in this video, I'm going to explain what is fluid features and also the dimensional analysis concept. So this is the overview of the topic that I'm going to explain later. And for fluid features, we are going to cover density, specific gravity, specific weight, surface tension, pressure, compressibility, vapor pressure, and viscosity. And we also look at what is dimensional analysis concept and how it is related to principle of homogeneity. So firstly, we will see what is fluid. So a fluid is actually a substance that has no fixed shape and will yield easily to external pressure. A more formal explanation is that there are three states of metal, which are solid, liquid, and gas. And fluid is either liquid or gases, or generally any materials that cannot sustain a tangential or shearing force when at rest, and that undergoes a deformation continuously when subjected to a stress. So therefore, solid doesn't fall in the category of the fluid because they cannot flow and also cannot resist shearing force. So now let's take a look at our first fluid features, which is density. And the symbol of density is rho. The study of fluid mechanics typically deal with a continuously flowing fluid or a small amount of fluid at rest. Therefore, it is more convenient to relate the mass or the weight of the fluid to a given volume of the fluid. Thus, the property of density is defined as the amount of mass per unit volume, or density is a measure of how compact the mass in a substance or object is. So we can see that the formula of density is rho equals to mass per volume, and the dimension of density are mass per length cube, and there are different units of density at different unit system, including the SI unit system and also the standard US system. And we can convert between the US system and also the SI unit system by substituting the equivalent of each dimension with the value here. So our second fluid feature is specific weight. So a specific weight is the amount of weight per unit volume of a substance, and it is usually denoted by the letter gamma, and has dimension of force per unit volume, and sometimes it is referred to as unit weight. And its unit in the US system and the SI system are lb per feet cube and Newton per meter cube, or kg per meter square times second square. And since the formula of the specific weight is gamma equals to weight per volume, so it is easy to indicate the specific weight and the density of the fluid by using that relationship. So the specific weight and the fluid density can be related by the gravitational acceleration, which is small g, and the relation is shown in the yellow boxes. So after we related the gamma and the rho, finally we will get specific weight is equals to density times gravitational acceleration. So next is specific gravity, SG. So specific gravity can be defined in two ways. So first, specific gravity is the ratio of the density of a substance to the density of water at 4 degrees Celsius. And secondly, specific gravity is the ratio of the specific weight of a substance to the specific weight of water at 4 degrees Celsius as well. So SG is dimensionless and it is defined as a ratio. And we can see that the usual standard of comparison for solids and liquid is water at 4 degrees Celsius, which is at its denser state and having a constant value. So therefore, the definition of SG can be mathematically expressed as here. And by substituting the constant value of density and specific weight of water at here. So in general, the density and specific weight and also the specific gravity of the fluid vary with temperature, usually decreases with increasing temperature. Hence, the property of the liquid at selected temperature can be referred to as appendix. So now let's move on to surface tension. The surface tension is the property of the surface of a liquid that allows it to resist an external force due to the cohesive nature of its molecule. So to make a surface tension too easy to understand, imagine you place a coin on a still water surface and it won't sink. This is because it is supported by the surface tension of the water. It's actually not significantly supported by the buoyancy because it will sink to the bottom if it is submerged. So mathematically, it is measured as the work per unit area required to move the lower molecules to the surface of the liquid. And dimension of the surface tension is force per length square. And the unit can be expressed in Newton per meter or pound force per feet. And the surface tension of the liquid, including water, varies with temperature. So next one is compressibility. Compressibility is measure of a relative volume change of a solid or a fluid in response to a pressure change. And the usual quantity that used to measure this phenomenon is the bulk modulus of elasticity or just simple bulk modulus E. And the formula is shown in the purple box here, where P is the pressure applied to the body and the delta V is represent the change in volume of the body due to the applied stress, and V is the original volume of the body. In the mathematical expression, a negative sign indicates that due to increase in the value of the pressure applied, the volume decreases. And according to above formula, the bulk modulus of elasticity units will be the same as the unit of pressure because the relative change in volume is unitless. So sometimes megapascal and kilopascal will be the SI unit of the bulk modulus of elasticity. And for information, liquid are slightly compressible, indicating that it will take a very large change in pressure to produce a small change in volume of the liquid. And thus the magnitude of E for the liquid will be very high. And gases are readily compressible but not usually applied using the term of bulk modulus. So now let's proceed to another fluid feature, which is pressure. So pressure is defined as the amount of force exerted per unit area of a substance or on the surface. Hence, the formula of the force of the pressure is force over area. And there are a lot of units of measurement that can be used by pressure, which are in the table here. But the unit bar and Pascal and sometimes ATM are more commonly used in the context of fluid mechanics or in the context of chemical engineering. And the two important principles about pressure are pressure acts uniformly in all directions on a small volume of fluid. And secondly, in a fluid confined by solid boundaries, pressure acts perpendicular to the boundary. So here are several types of pressure measurement devices, including manometer and also barometer. And the simplest kind of the manometer is the U-tube. Then we will also have differential manometer that used to measure the pressure between 2 points, but not the actual value of either one. And also inclined well types manometer, and the device that used to measure the atmospheric pressure is called barometer. So now let's look at vapor pressure. The vapor pressure of a liquid is the equilibrium pressure of a vapor above its liquid in a closed container, and it increases with temperature. So Clausius-Clapeyron equation and also the Antoine equation are the examples of the formulas to calculate the vapor pressure of some substances. So the Clausius-Clapeyron equation relates the vapor pressure of a compound at two different temperatures using the enthalpy of vaporization. However, the entire equation is derived from the Clausius-Clapeyron equation, and it is describing the relation between the vapor pressure and the temperature for pure substance. So finally comes to our last fluid feature of the video, which is viscosity. So the viscosity is the internal friction of a fluid caused by molecular attraction, which makes it resist a tendency to flow. And viscosity are divided into dynamic viscosity and also kinematic viscosity. So for dynamic viscosity, it is the resistance to movement of one layer of a fluid over another. So in order to understand the formula in the blue box, you can refer to the diagram beside the blue box. And you can see the letter like middle J is shear stress, which what we call is tau, and it is the force required to slide one unit area layer of the substance over another. For a common liquid, the magnitude of the shearing stress is directly proportional to the change of velocity between different positions in the fluid. Then it's important to mention that when a thin layer of the fluid is flowing between two surfaces, the fluid in contact with the non-moving lower surface has zero velocity, and that contact in with the moving upper surface has the velocity same with the moving surface. Then the velocity of the fluid vary in a straight line manner. Therefore, the velocity gradient is a measure of the velocity change, and it is defined as delta v over delta y, and what we call it shear rate. And the shear stress tau is directly proportional to the shear rate. Therefore, we develop our first formula, which is n like letter, and what we call it eta. And eta is the constant core dynamic viscosity of the fluid. And then we rearrange the first formula to make eta as a subject, and the higher the eta, the higher the viscosity of the substance. And the SI unit of the dynamic viscosity can be Pascal times second, or Newtons times second per meter square, or kg per meter times second. So now let's continue discuss the kinematic viscosity. And many calculations in the fluid mechanics involve the ratio of dynamic viscosity to the density of the fluid. As a matter of convenience, the term kinematic viscosity, which is represented by Greek letter nu, is used. And kinematic viscosity is a measure of the resistive flow of a fluid under the influences of the gravity. And the SI unit for kinematic viscosity is m squared per second. So this is just a subtopic of the viscosity, which is the distinction between a Newtonian fluid and a non-Newtonian fluid. So any fluid that behaves like this diagram here, we discussed on the last slide, is called Newtonian fluid. And look at the figure 1. The slope of the curve is a measure of the apparent viscosity. So a Newtonian fluid has a linear line, meaning that the slope and the viscosity is constant for a Newtonian fluid. Therefore, the fluid where the shear stress is directly proportional to the velocity gradient with a constant viscosity is called Newtonian fluid. However, the slopes of curves that are vary are called non-Newtonian fluid because it indicates how apparent viscosity changes with the velocity gradient or the shear stress applied. And the examples of the non-Newtonian fluids are Bingham fluid, pseudoplastic, and rheopactic, and so on. So two major classifications of the non-Newtonian fluid are time-independent and time-dependent fluid. And time-independent liquid has a viscosity at any given shear stress that doesn't vary with time, but viscosity of time-dependent fluid changes with time. So this is the end of the part for fluid feature. So now let's move on to talk about dimensional analysis. So the study of the relationship between physical quantities with the help of dimensions and also the unit is termed dimensional analysis. So it involves the study of the relationship between different physical quantities by identifying their fundamental dimensions. But what is fundamental dimension? So you can see the table here, up here, are the example of the fundamental quantities. It is an independent quantity including the example like mass, length, time, and so on. Then the derived quantity are those physical quantity that are derived from the combination of fundamental quantities. Density, velocity, and force are the example of derived quantity. So it is important to know that dimensional analysis is fundamentally based on the principle of dimensional homogeneity. So the principle of homogeneity state that the dimensions of each of the terms of a dimensional equation on both sides should be the same. And this principle is helpful because it helps us to convert the unit from one form to another. And to better understand the principle, let us consider the following examples. So the equation used here is S equals to ut plus 1 over 2 at squared, where S is the displacement, U is the initial velocity, V is the final velocity, A is the acceleration, and T is the time in which changes occur. So first we consider the dimension on the left hand side, which is the length, and then consider the dimension on the right hand side, and we write out the dimensions for each terms on right hand side. Then we cross out the same one, and please be reminded that the pure numerical factors or number in this case is 1 over 2 has no dimensions, therefore it can be ignored. So since the dimension on the left hand side and the right hand side are the same, hence by the principle of the homogeneity, the given equation here is dimensionally correct. So therefore, you can apply the dimensional analysis to check the correctness of a physical equation. So let's say you can't remember whether time is equal to speed over distance or time is equal to distance over speed. We can check this by making sure that the dimension on each side of the equation are matched. So you list out the dimension of on both sides of the equation, and as long as the dimension of on the left hand side and also the right hand side are the same, which means you can determine the correct equation to be used. And besides, you can also apply the dimensional analysis to perform unit cancellation procedure. So the analysis required in fluid mechanics involve the algebraic manipulation of several terms. Therefore, the unit cancellation procedure is here to ensure proper units in any kind of calculation. And it involves ensuring that the units are consistent and properly accounted for when performing calculation, particularly in converting from one unit system to another or verifying the correctness of an equation. So now let's see what is dimensionless quantity. So dimensionless quantity is the quantities that doesn't possess any dimension, which means it is a unitless or a scalar number resulting from computational using the same dimensional quantities. A few of them are radian, atomic mass, specific gravity, and etc. So we can see the example here is relative density. So for relative density, the density of a liquid is compared to the density of water, and both units are the same. Then they can be cancelled each other, and therefore the relative density is a dimensionless quantity. Lastly, dimensional analysis is really important because by applying the homogeneity principle, dimensional analysis is essential to keep the unit same, helping us perform mathematical calculations smoothly. Besides, it is also able to check the consistency of a dimensional equation and to derive the relation between physical quantities in physical phenomena. And it is also able to change units from one system to another. However, the limitation of dimensional analysis is that the formula containing trigonometric function, exponential function, or the logarithm function and etc. cannot be derived. Finally, it comes to the end of my presentation, and this is the references I used to complete my report and my presentation. And thank you for listening.